People at home, can you read the board? Okay, great. All right, let's move on. We have discovered our first reaction. That is a electrophilic addition to an alkene. We did it by adding HCl to ethene. Okay, let's just explore that reaction a little bit more by doing some more examples. Let's take 2-butene and hydrogen bromide. And as long as it's still a gas, it's still covalent. It's not dissolved in water, so it's not ionic yet. If you treated it as being ionic, you could reach out and have a definite electrophile, an H+, and a definite nucleophile, a Br-. Okay. So 2-butene. Oh, hold on a minute. 2-butene. Which one do we need? Because there's two different types of 2-butene. Is this going to make a difference? I'll do the top one, you're responsible for the bottom one. And we'll figure out at the end, is there any difference? Arrow comes from the middle of the pi bond, reaches out to the most electropositive thing that it can find. That's the hydrogen that's on the losing end of the HBr bond. It generates another bond to break. So my middle looks like this. I've taken the double bond, it's down to a single bond because I've broken the pi component. But now the question arises, which one of these two carbons is going to get the new hydrogen? That one or this one? Doesn't matter. If your starting reactant is symmetrical, there's not any preference. Okay, so pick one. If I put the hydrogen here, that means that the positive goes on that carbon. And if the positive goes on that carbon, curved arrow, new curved arrow, from the area of high electron density, the thing that is negative, the thing that has a lone pair of electrons, to the area of low electron density, the thing that is positive, has the positive charge. Okay, now there was already a hydrogen there, and a bunch of hydrogens here, and a hydrogen there, and 3 hydrogens here. We just didn't write them in. And then that gives me this. So my product is 2-bromobutane. If I start with the trans isomer. Trans isomer and the cis isomer. I've said this is symmetrical. I mean, technically, it's not. This one definitely is. It's symmetrical if we were to write it out in a plane, but the grouping here is the same as the grouping there. My electrophilic addition occurs by heterolysis. The red part is my electrophile. The blue part is my nucleophile. And they add across the place that was the original double bond. The original double bond was between carbon 2 and carbon 3, and my electrophile and nucleophile, the H and the Br, have come in on carbon 2 and carbon 3. Could have been the other way around. I could put the hydrogen on this one and have the bromine be over there. I would just switch the numbers around. When 2 groups are next to each other, when they're next door neighbors, we say that they are vicinal. And what we see here is that those groups have added on neighboring carbons. It also looks like one is up and one is down. That might just be a consequence of the way that I've drawn my sketch. I think we'll have to investigate that a little bit more before we can say that if that's true or not. Okay, all right, do the bottom one. Do the bottom one and tell me simply, same or different? Does starting with the trans isomer over the cis isomer have any impact at all on what it is that I get as a product? That's a valid question. Just want to know same or different. What I also want to know is how many left-handed people do we have in class? You're the majority. And we've got a couple who are also lefties who are not here. Wow. Same or different? Who's finished? People at home, there is a poll. In the room, the people at home can't see you. Same or different? Show of hands. Same. Show of hands. Different. Okay. I don't know what the answer is yet. I haven't looked. Okay, people who think the answer is different. Oh, I think I'm confused on which hydrogen to add to the nucleophile to. Nucleophiles add to carbons. I think you might have just asked that question wrong, Becca. People who think they're different. Give me a reason. Any reason. Did you say different? Why? Okay, that's fine. Because it still this. Ooh, okay. Marcel. To be trans, you need two groups that are the same as each other on opposite sides of the double bond. To be cis, you need two groups that are the same as each other on the same side of the double bond. If you don't have a double bond, the cis to trans notation goes away, unless you're a ring. If you're a cyclic ring, we bring it back and we allow you to be cis or trans on the face of a cycloalkane. All right, so let's just sketch this out and see if it makes sense. Here's my framework. That framework has not changed. The sigma bonds have not moved. Only the electrons that were in the pi bond have moved. And that means I have hydrogens here. I have a hydrogen there. I have a hydrogen here. And I have 3 hydrogens there. Okay. This molecule is symmetrical. It means there's no preference of where this first thing goes, so pick one, left or right. We did this one on the left, so put that one on the left. That bromide, electrons come to it, making it negative, so the bromine becomes a bromide. I thought that was something that had no charge. I've generated a negative. That means I have to have a positive somewhere in my picture to balance that out, right? I look around and I see all my carbons have 4 bonds. Wait a minute, that one doesn't. That's where my charge goes. And then this curved arrow goes, well, and I've made this. Now, the question is, are they different? What would the name of the bottom one be? If the top one is 2-bromobutane, what would the bottom one be? This is also 2-bromobutane. These are both 2-bromobutanes. So are they the same? Is there something I'm missing, or are they just the same? Looks like they're just the same. Doesn't matter whether you start out with cis or trans, or maybe it does. Maybe we just haven't asked the right question yet. Because. That carbon, and indeed this carbon, are hiding something. What are they hiding? What is special about the carbon with the little red circle around it? The chiral. Thank you, Janet. Thank you, Marcella. This carbon has a bromo, a hydrogen, a methyl, and then an ethyl. This one has a bromo, hydrogen, a methyl, and an ethyl. They're chiral. Oh, the product's chiral. Did one of them make the R and one of them make the S? This is where you stare at this for a second and imagine these things in 3 dimensions. Our starting material, the reactants, have something that our products don't have. Our products have something that our reactants didn't have. Our products have chirality. Chirality arises if you have 4 different groups around a tetrahedral, 3-dimensional carbon. But these are planar. They're flat. I really should have something better than this. It was the first thing that came to hand. If this is my reactants and it is flat, it's flat. And this is a bromide. Can the bromide do this? Yeah. Could it also do that? Yeah. So let's say it is possible to make the R or the S isomer. Under what's going on in the board, is one of them favored? You get both. This could be the R, could be the S, but this reaction is not going to dictate which one of those 2 isomers you're going to get. So you get an equal 1-to-1 ratio of enantiomers. And a 1-to-1 ratio of enantiomers has a special name. Who's read the special name? What's the name that we give to a mixture of stereoisomers in equal proportions? If the R bends one way and the S bends the other, a 1-to-1 ratio of both of them, the light passes straight through the middle. Technically, technically the trans is not symmetrical. But what I meant when I started saying it was symmetrical is if I wrote it out this way, really, really simplified, then it's symmetrical. The cis one definitely is. Trans one, it's got symmetry, but we would have to learn how to recognize it. Okay. These are what we call a racemic mixture or a racemate. So the good news is I can use this reaction to make molecules that have special hidden properties. I can make chiral molecules out of this. The bad news is I didn't succeed on my first attempt. Okay? I didn't succeed on my first attempt because there was nothing pressuring the reaction to choose either of these carbons. Both of these carbons in the eyes of this reaction are equal. This carbocation, this is all getting a little bit scribbly, is what we call an intermediate. And carbocation intermediates are very, very important. They are often the reason why, if you can have more than one product, one of them wins and the other one doesn't, which is what we're going to do now. Let's do that again. We're going to change the molecule. I could have actually left everything that's on the board on, only it was looking a bit scribbly. Because all I'm going to do is add a methyl. There's my 2-butene. Just this racemic mixture or racemate. I'm going to write it out a different way this time, so you see it two different ways. A racemate or a racemic mixture is a 1-to-1 R to S mixture. And it has no optical rotation. Oh, by the way, I'm almost done writing your lab. Thank you for the Thursday people. Thursday people came in and did a great job. They added to the stuff that the Tuesday people did. And we've got a really good set of data. And I'm like 2-3 questions away from publishing that lab. Not in any particular hurry to get it back. You know, so this lab's only a quiz. If you had the R, it would bend one way. If you had the S, you'd bend the other way. If you have them both together in equal amounts, the light goes straight through, does not rotate. Okay, here's my 2-butene. Changed it. What's the name of this? People at home, type in a name. Plus, I'm going to change this back to, just so we see something different. People at home, give me a name. Thank you. 2-methyl-2-butene. Thank you. I think everybody got all the hyphens in there as well. Yeah. Okay, so if I wanted some 2-methyl-2-butene and I called up the manufacturer and I said I would like some 2-methyl-2-butene, are they going to ask me that horrible question that I'm never prepared for about which one? Oh, camera goes fuzzy if you stand in front of it for too long. Oh, shoot. That was not the right button. Oh, no. Getting there. Okay, I'm going to ask my question, the same question, a different way. Is this the cis or the trans? It's time for a poll. There are 3 possible answers. Is this the cis or the trans? It's taking a minute to sink in, but we're getting there. Is this the cis or the trans? The answer, of course, is no. No, it is not the cis or the trans. These 2 groups are the same as each other. If you have 2 groups that are the same as each other on one side of the double bond, then there can be no preference on the other side. Not cis, not trans, even better. Asymmetric. Asymmetric reactants make the reaction. Pick a choice. They're going to make this reaction develop a decision midway through, and it's going to happen at the intermediate. So, this is only one reactant, but there are 2 possible answers. HCl. I changed it from HBO. Reaction starts the same way. The electrons from the pi bond, that's where my electron-rich part is, reach out and grab hold of the most positive thing that they can find. That's the most positive thing because it's on the losing end of that polar bond. All right. Something happens now. That hydrogen either adds to the carbon on the left or it adds to the carbon on the right. Hydrogen is only allowed to make one bond at a time, so if I make a new bond to it, the hydrogen has to let go of a bond it's already using. The pair of electrons that are in that bond go back to the chlorine as a lone pair of electrons. That chlorine becomes a chloride. If I've got a negative in this reaction step, but I didn't have any negatives here, it means I have to have a positive to balance it out. So the positive goes either here or here. Same or different? You don't have to draw all this detail in. What I want to get to is that there's an additional hydrogen right there. Products are different to one another. They're so different, they have different names. This one and this one have different names. Longest chain is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Whichever way I look at it, it's only a butane. I've not invented, and I started with the bute, so I'm not going to add an additional carbon. The number of times that we do a reaction in this book, and we either add a new carbon or delete an existing carbon is very, very rare. When it happens, it's going to be a massive deal. If we change the number of carbons in the backbone of our molecule, it is going to be a really big deal. Okay, I have, so if this is 1, 2, 3, 4, then I have a methyl at 2 and a chloro at 2. This gets to be 2 chloro, 2 methyl. Butane. The one at the top is 1, 2, 3, 4. It's either 2 chloro, 3 methyl, or 2-methyl-3-chloro. In fact, I'm still saying it wrong. It's either 3-chloro-2-methyl or 2-chloro-3-methyl. Any opinion on which one it should be? It really doesn't matter desperately. Whichever one you use, if you wrote that name down, I would be able to decipher. I would be able to draw the correct sketch on either of those two names. But there is a school of thought that says, tell me where the branching happens in the molecule before you tell me where anything else happens. Unless it's as a functional group. If it's an alcohol, that's an OH or something else that has its own functionality, then it definitely, if it changes the name, then we go with it. So this is probably 3-chloro-2-methyl. Okay, they are different from one another. Let's see if I can predict the relative amount of these that gets made. Excuse me. If I do this reaction, both of these pathways are open. They could both happen. One of them occurs more than the other one. Does one of these look better than the other? Does anything just jump out at you and say, I don't know, I can't really quite say what it is, but one of them looks nicer, looks better? The primordial part of my brain likes one of these more than the other.
Yeah, 3-chloro-2-methyl just looks nicer to me.
Okay. I've got people chiming in. The top one. So the top one looks more balanced, doesn't it? Look, the top one looks more balanced, and the bottom one looks more lopsided. All the stuff is gathered over here. Okay, here's how we know. The decision of which one of these gets made did not happen here. And by the time that we get to here, it's already happened. The decision about which one of those two products is the best happens in the middle. It happens at the intermediate stage. One of these is significantly better than the other. Significantly better than the other. And it comes down to the stupidest question anybody has ever asked. Let me see if I have one. Oh, I don't have one. So what I have to do for the people playing at home is this. Nice colorful one. And then go plus, plus, plus. Ooh, look at that. And then I have to go back and I have to no, it's not files. Is it here? Chrome tab, there you go. Chrome tab, periodic table. Here's periodic table. People at home, can you see it? We can't see your chat box anymore, so you're going to have to use.
Yeah, we can now.
Okay. Dumbest question you're going to hear today. Which side of the periodic table is carbon on? Look at the periodic table. There's going to be a poll. Look at the periodic table. Identify which side of the periodic table carbon is on, because that is going to settle the argument that's currently on the board. Okay. Oh. Come on, polling. Make it happen. Off you go. Which side of the periodic table is carbon on? I need everybody's answer. It's obvious, right? It's obvious. When we look at the periodic table, we can see where carbon is. This is a dumb question. It is the answer to our problem, the one that's on the board. The answer is obvious, unless, of course, I hadn't thought about it correctly. What group is carbon in? 4. How many groups on the periodic table? 8. 4 strikes me might be halfway to 8. So that could be an invalid poll. Poll needs more answers. There are 8 groups on the periodic table. Carbon is in group 4. 4 is halfway to 8. So it strikes me that there should be 3 possible answers to this question. I should be a politician. I can make people change their mind so easily. I should be a politician. Not allowed to, I'm not even allowed to vote. You will go out and make a because of the felonies.
Oh, really?
I'm not American. No one had noticed? No, I'm a guest here. Can you all see the board? Yes, right? 1, 2, oh, that ain't gonna work. Over the blast shirt.
Oh.
It's an A&M win weekend. Calling it now. A group's on the periodic table. Carbon's in group 4. These 4 groups are on the left of the periodic table. Those 4 groups are on the right of the periodic table. Carbon is on the left. Carbon is on the left of the periodic table. Here's what we know about the periodic table. Everything on the right side of the periodic table is electronegative. It pulls electrons towards itself. Carbon is not on the right side of the periodic table. It's not going to pull electrons towards itself. It's going to push them away. Carbon pushes its electrons away because carbon is on the left-hand side of the periodic table. Here's positive charge. This carbon is going to push electrons towards it, as is that one. So I have a positive receiving electrons, shouldn't have to remind you electrons are negative, from 3 places. This positive is only receiving electrons from 2 places. As a result, this top positive charge diminishes in size somewhat, but the bottom one gets to be smaller. The positive charge is your target. It's the thing that causes the reaction. Having a smaller target makes you more stable. This one at the bottom is the better carbocation. So when I do this reaction side by side, I'm expecting close to 100% for this bottom one. Some of that might get made, but this is going to win. It might be in the high 90s. This one wins, and it's all down to something called carbocation stability. We're going to spend Monday talking about carbocation stability, and then figuring out how that then becomes a rule. Because if this is all or nothing, when I see my reactants, I don't have to write this other one out. I don't have to write 2 equations out and say, well, which one of these looks best? No, I just go, that one wins. And I draw only one of the mechanisms out. We're going to learn how to recognize it. We've just learned why. Most people don't know why. They just know how to recognize it. That's all on Monday. Okay, there's a homework posted and there is a quiz posted. The quiz is hand-drawn structures of isomers, some of which are a callback to what was on the exam. Why would a professor give you the same kind of question that was already on a previously existing exam? That was the question that you didn't do well. As a class, the worst question on the free response part was drawing the Newman projection of the cyclohexane. Many, many people stumbled on that one to different degrees. Nobody completely screwed it up, but everybody got it, lots of people got it the same way, a little bit wrong. So you get to do it again. And then the quiz that's due is easy cis-trans on alkenes, and we haven't done any of that yet, or before. Okay, So keep an eye on Blackboard. Got the whole weekend in front of you. Vanessa. Quick question. Exam 2 will cover, I don't even know what the numbers of the chapters are. Vanessa, I will give everybody a complete rundown before it happens of what the test contents are, okay? From alkenes forward. Shoo. Have a good weekend. Thank you, Stephanie. See you all next week.